Okay, well, we know that we're going to have to take into account the number of calls to partition for each phase, which is xj, and we're going to have to take into account the amount of work done by partition. Is there really anything else we need to take into account? There's actually nothing else we need to take into account. Well, one other thing, actually, sorry. It's the amount of data passed into partition. But other than that, we don't have to take anything else into account because, like we talked about, all the work is done in partition inside that for loop. So here's our total running time of our select. Total running time is summing over all phases. So I don't have a definite summation here where I can tell you that we're going to be in phase 0, 1, 2, 3, 4, 5, all the way up to 10, because the number of phases depends on the input. So you can think of this as looping over all phases out to infinity. And we'll end up with the same result regardless of how we have notated that. xj denotes the number of calls. Let me just put this all out there together. So xj is the number of calls in a phase. It's not an indicator variable, so we could have 0 calls in a phase, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It depends on the input size again. C is a constant for the amount of work done by partition. So maybe partition does 10n amount of work. So C would be 10. Here's an interesting part here. In a given phase, this is an upper bound on the amount of items or elements we have in that phase. So where do I get that as an upper bound? So if I'm in a specific phase, this is my notation for how many elements I have, and the upper bound is this part. So I'm just going to take that upper bound and say worst case scenario is I have the maximum number of elements for that phase every time I call it. We know that's not really possible, but it is an upper bound. So let's say I'm stuck in phase 6 for 12 recalls. Pretty unlikely, but let's say that's true. This is the maximum number of elements I could have for each one of those 12 calls, and in fact I'll probably have less than. But that's okay because I have my inequality here. So what is C times 3/4 Jn? That's the total amount of work during a single call in phase J. And then we just multiply that by xj to get the total amount of work in a given phase, sum over all of our possible phases, and now we have the total work done by our select. All right, well, let's dig into this. Why is this phase notation useful? It just sounds sort of made up. Why do we care about phases? Well, we will leave a phase when our pivot element is within the 25 to 75 percentile middle part of the subarray. So if we choose a pivot element, somewhere in that middle 25 to 75 percentile. So why is that? Because if we do that, that means that both the left-hand sides contain less than 75% of the data, which means that we'll be outside of this range, the 3/4 range. So the 3/4 deliberately sticks us sort of inside this middle. So if you might have been wondering where did I get 3/4 from, that deliberately sticks us, making sure that we end up with a pivot element inside that middle 25 to 75 percentile. Okay, so let's see sort of why that is. Well, if I pick something, so let's say here's the middle 25 to 75 percentile. Let's say I pick this as the pivot. Well, I could have to search either side. We know that there are at most going to be 1/4 of the elements here and 3/4 of the elements here. So I still have 75% of my input remaining. Or if I pick an element that's here as pivot, I could end up with this 75% of the elements I have remaining. So this entire idea of a phase is built up really on, did I get a good value for the pivot? And if I got a good value for the pivot, then I move on to the next phase. Or I skip over some phases depending on how good of a pivot choice it was. Okay, well, what's the probability? And this is really, again, why we care about 3/4 here, why we care about this 25 to 75 percentile. It's because it makes this part really easy. What's the probability that we choose a this should say pivot, a pivot in that middle range? So from the 25th percentile to the 75th percentile. And our notation here again, the open parenthesis just means it's exclusive on the lower bound and inclusive on the upper bound, just like I should have had right here. Okay, well, why do I say that that's an easy probability? Well, there are 50% of the elements in that span. So I have a 50% chance to choose a good pivot. So a 50% chance to choose a good pivot element. which means that we leave the current phase. So we've reduced our problem really to the coin flip. So another way to say this is the expected number of times that I'm in a phase, because there's a 50% chance of leaving the current phase, the expected number of times to be in a phase is less than or equal to the number of coin flips it takes to get heads. So what do I mean by that? Well, let's just say if we get heads, that's a good pivot. It's somewhere in that middle 25 to 75% range. Anything outside of that range, like a minimum value or a maximum value or something close to one of those two extremes, that's going to be a tails, that's going to be a bad pivot choice. So let's let n be the number of flips you get until you get a heads. That's a geometric random variable, and it looks like this. So we know that we have to flip the coin at least once, and if we have to flip it again, there's a 50% chance that we'll get it on the next the next flip. So we have to flip it at least once, and then there's a 50% chance that we'll get ahead on the next flip. So we have to figure out from this series, what will this evaluate to? What's the expected number of flips? Well, if I plug this equation in to itself, it's a sort of a recursive equation here, I get 1 plus 1/2 plus 1/4 e, and you can keep plugging it back into itself, and what you end up with is the expected number of flips to get a heads is 2. I don't happen to find this to be a very intuitive way to figure out that it's 2. So let's look at this another way. Let's look at it using our probability from a few class periods ago. So what is the expected number of heads per coin flip? So you can think of this as an indicator variable. A 1 indicates that we got a heads, a 0 indicates that we didn't get a heads. There's a 50% chance we get a heads, 50% chance we don't. So the expected number of heads per flip is 1/2. And what we can say is, well, the total number of heads is equal to the expected number of heads per flip times n. And what we have to do is solve for n. So the total number of heads we want is 1. So we'll say that 1 is equal to, and we just said the expected number of heads per flip was 1/2. So we have 1 n over 2, and we solve that for n now, and we get n is equal to 2. I find this to be a little bit more intuitive way to figure out, well, how many flips do I need to have expected at least 1 heads? All right, so back to our proof here. Instead of figuring out the total running time, we're going to figure out the expected total running time, which means I've got the expected value for this flip here. And I can use linearity of expectations here instead of having an expected value on the outside here. All right, well, there's something special we know about this quantity, and that's that it's, the point here is what I just made, it's that the expected value of their total running time, I could put the e out here, but given linearity of expectations, I can just put the e on the inside here. Well, there's we know something specific about this. It's the number of times you have to flip a coin to get a heads, and that's going to be equal to 2. So I can just plug 2 into that equation. And when you plug 2 into the equation, it doesn't depend on j, so I can just pull it out. So I got 2cn times the summation of 3/4 j. Well, this quantity here is something we've seen before also. When we were looking at the master method, we saw that that's a geometric sequence, and whenever this ratio, so that was the ratio of a over b to the d power, if you remember, that ratio, whenever it's less than 1, evaluates to being less than or equal to 1 over 1 minus r. Well, when you plug in 3/4 and for r, you end up with 4. So that just converges to 4. Okay, so what does this mean? It means that the expected total running time is equal to 2c and 4. I'm going to combine the 2, the c, and the 4, and we'll just call that c combined. So we have c times n, which is big O of n. So what does that mean? The upshot here is that the average running time of quick select, or r select, or randomized selection, whatever you'd like to call it, is big O of n.